Thank you. Thank you. I'm going to let y'all go back to work on this problem in just a second, but I want to talk about this bell ringer because this bell ringer is exactly what I needed to address based on your test, and we need to improve our understanding of this before the midterm next week, and hopefully this will, there we go. So, this equation that I created, this first one here, it helps if I have a marker. Can you give me one of those purple? Yeah. Don't know me. I actually found some purple chalk that I'm going to start using once it comes in on height. Alright, yeah, I don't know if you can tell, but my favorite color, guesses? Purple. Purple, yep, I mean, so I didn't have a ton of purple chalk, so like I have a box of blue chalk, but I didn't find a box of purple chalk until recently. But it's definitely purple, like, it's literally like the color of royalty, it makes me feel good. Anyways, so f of x equals 3 times 2 to the x minus 5 plus 3. So looking at this equation, we got a little bit of a split here, and we got majority here that say exponential function and a couple that say quadratic. And I need us to pay attention to this because we have to understand this detail. First off, on the test I asked you to identify what mathematical representation this is. What is it? Algebraic representation. How do we know? Remember, you got to justify your answers. How do we know it's algebraic? It's a what? It's an equation with variables and with numbers, right? Like, we need to be able to recognize that it's not a problem. Everything can be a problem, Miles, right? We're talking about an algebraic because it's an equation. So, what do we see here, right? A few of us said quadratic. Why were some of us thinking quadratic? Say it again, Leah. They just saw an exponent, right? So that exponent is critical, and I need us to remember this. To be quadratic, what do we need to see in that exponent? A square, right, at 2? Do we see a square in this exponent? No. It has a base of 2, right? But what's in the exponent with this one? So a variable, right? Guys, when we have that variable in the exponent, that indicates that we are constantly and repeatedly what? Multiplying. Is there a whole lot going on in this one that we haven't played around with yet? I mean, have we done an x minus 5 or a plus 3 here? We have not done that. So there's extra stuff here. But fundamentally, and this was the assessment that I was trying to see, do you recognize that there's a variable in the exponent? Because if there's a variable in the exponent, what is it, Peyton? If there's a variable in the exponent, what type of function is it? Okay? Davian? What is it? Exponential? If there's that variable in the exponent, it is an exponential. Peyton? Exponential. It doesn't matter how complicated other pieces get in there, it is an exponential function. So that requires us to address this. Is it vertex or factored form? Why not? We need to remember this detail. Okay, so the variable's in the exponent, so but why is it not vertex form or not factored form? Any ideas, Elizabeth? Okay, so but we're getting closer, right? Standard form and factored form don't have variable exponents because, Brianna, what do we mean we're talking about when we say vertex form or factored form? Not sure? Bella? It's not squared. We're super close now. What do we mean when we say vertex form or factored form? We're talking about what type of function. There we go, right? Like, if we say vertex form, it's called vertex form because it has a vertex, it's a quadratic function. When we say standard form and we say factored form, when we say vertex form, really we need to say of a quadratic function. This isn't quadratic, so can it be one of these forms? You can only say those forms when you're talking about a quadratic. Technically, every polynomial has a standard form, but now this was the trickiest one for a lot of us, and I did not mean for it to be a tricky one, but this did give me a lot of insight into what we understand about this function. Hey guys, what does this look a whole lot like? Looks a whole lot like vertex form. But what's it missing? Guys, if it doesn't have a square, is it quadratic? No. So we can't call it vertex form. we need to recognize this because a lot of us miss that on the test. If there is not a square, it is not a quadratic function. What type of function is it? That's linear. The highest thing or the most important thing here is that multiplication. Because there's no square, I could have distributed. And that's a linear function through and through. Okay? So I need y'all to remember, and so this is, we got to keep in mind what the differences are between those different types of equations. If it's a quadratic, what does it have to have? A square. If there is no square, what's it not, Peyton?
Oh, quadratic.
Thank you, there we go, right? That's something you know, right? If there's no square, it is not a quadratic. We all go with that? All right. We've got to recognize these details about those equations. I'm going to give y'all's test back probably tomorrow, because I finally got the last person to take their test, and we'll talk about a couple of other details. But keep that in mind. We got to continue working on these things. All right, get back to working on this quadratic equation, trying to solve it.
Yeah, I did know. I can work it. So did I.
What methods do we have available to us to solve this quadratic equation?
Quadratic formula.
Quadratic formula and vertex form, right? Why can we not factor this one?
They don't equal negative 2.
Say again.
The product of A times C doesn't equal negative 2.
So the product of A times C did not add up to B, which should make sense. I want y'all to look really quickly over there, right? If you didn't use the vertex form, we want to notice what is our H in this problem? H is 1, right? Once you calculate that opposite of B divided by 2A, what's K? And then this parabola is concave up. So it's really beneficial to understand how to get that vertex. Because what do we see right away from here? Because this will be on your assessments, being able to look at a graph and know what type of roots you have. How can I know from here that I can't factor it? There's no x-intercepts. Bella, what type of roots are we going to have if there's no x-intercepts? Imaginary, right? We need to recognize that if it intersects the x-axis, those are our real roots. If it does intersect the x-axis, we're going to have what kind of roots? Imaginary, right? No, so I do want to point this out. X-intercepts are only the real roots, right? X-intercepts are only the real roots. But if we have imaginary roots, how many roots do we still have? We still had 2, didn't we? And that goes to the concept that a second degree polynomial always has 2 roots. Does anyone remember what that's called? It's pretty fundamental to algebra.
What's the price later?
Say again?
What's the price later?
It's pretty fundamental to algebra.
What's fundamental?
The fundamental what? Theorem of algebra. It's pretty fundamental to algebra, guys. Fundamental theorem of algebra, an nth degree polynomial has n roots. So a second degree polynomial has 2 roots. A third degree polynomial has a 4th degree, 75th degree, 75, right? That's that fundamental theorem of algebra. Which group is not full since I collected the cards? Y'all as well?
I'm just
Oh, so join the queens. Okay. But the jacks typically only have 2, because remember I took the 2s and I made them jacks because it's closer to be able to see everything. The 2s just are like away in the corner and it's tough for them to see stuff. All right. So fundamental theorem of algebra, we got to know that, but let's come back to here because we got to talk about this. This is where some of us are running into some trouble, and if we don't master this detail, it's going to cause us trouble later. So these groups used the quadratic formula, right? We're going to talk about the vertex form over there in a second and compare these two. But right here, when we get to this point, this is usually where people run into trouble. So what's giving us trouble with that right there? The square root of -4, is that what you said?
Yeah.
Yeah. So how do I deal with that square root of -4? We square root it, but how? What happens if you type square root of -4 in that calculator?
Do we put 2 on?
See, that's where we need to talk about this a little bit more. So that's some good thinking there. I like that. Does anyone remember how we talked about this yesterday, what I do to rewrite this radical to be able to evaluate it? I rewrite this radical to make it easier to evaluate it.
Did you put it in a fraction?
So yeah, that ties into it. So hold on a second. Yesterday we looked at taking the square root of a fraction, right? And I pointed out, hey, I can just take the square root of 64 and the square root of 9, which gave me 8/3. How can I apply that here? Yeah, I'm going to eventually get there, but how do I know, like, how do I get to that point? Say again. Say it louder. So what times itself equals 4? Sorry, I'm just not quite hearing you. You're so quiet on me. Come on. So I will say this. 4 times something.
-1.
4 times -1. That is -4, is it not? That is the same thing? So remember how I was able to rewrite my fraction as 2 different radicals? Or 2 different roots? So how am I going to apply that here?
4 over -1.
Well, I did that here because it was division. Am I dividing these things? So what am I going to do? So I'm going to multiply. What am I multiplying?
Square root of 4 times square root of -1.
Remember, I talked about it yesterday, is that you can split it up into your factors. That's it. If you can rewrite it into factors, then you can split it up into those factors. What's the square root of 4?
2.
What's the square root of -1?
I.
So 2 plus or minus 2i, all divided by 2. I'm going to give you one more example like this before we get started practicing this some more. But let's say I had the square root of -18. How could I rewrite this one?
18 times -9.
Okay, 18 times what?
-9.
-9?
What?
-1.
Let's say, it needs to equal -18, doesn't it?
That's what I'm doing.
That's what you meant. I got you. Now, I will point out, we do want the -1 in there because what's the square root of -1? I. We always want the square root of -1 because that's going to give us our I. But I'm going to pause and slow you down here. I'm going to point out we could rewrite 18 as well. Because what am I trying to do? I'm trying to take a square root. Are there any factors of 18 that I can take the square root of? Okay, so I'm going to rewrite my 18 as 9 times 2 times -1. I'm going to find every perfect square I can, and now I'm going to take that square root, and how am I going to rewrite it? I don't have a fraction.
Oh. I said, you said anxiety. Never mind.
Hey, I'm going to rewrite it. It was another F word. I'm going to pay attention to my factors. How many factors do I have? 3. So how many radicals am I going to have?
3.
What are they going to be?
Now,
Square root of 9 times square root of 2 times.
Square root of -1.
Okay, take the square root of whatever you can. Do I know the square root of 9? Yeah, what is it? 3. And I'm only going to take the square roots that give me integers. Square root of 2, if you type that in the calculator, it's like a 1.414. I only know that because square root of 2 is a really common one. I've played with it a lot. But it continues past that because the square root of 2 is going to be what kind of number? Irrational, right? It's only going to be an irrational, or it's going to be irrational, so I'm going to leave it like that. And then square root of -1. I. Every time you see that square root of a -1, it's I. That's all you do, right? You split it into those factors, what you can take the square root of, what you can't, and then you're -1. Don't make it harder than that. Now, I do need to finish this, right? This is all supposed to be, by the way, when you do your standard, or your quadratic formula, please make sure you say x equals. The whole point is to find those zeros, right? Quadratic formula, x equals. I don't think I saw anyone with the quadratic formula saying x equals. Oh, no, we got one. Proud of y'all. Make sure when you do quadratic formula, you say what? X equals. Okay. Can I simplify this at all?
No.
Not at all? Yes?
Teachers and students, please
No.
excuse this interruption.
I
At
got
this
something
time,
to
we
teach.
need all freshmen
Oh, thank
who
goodness.
are going on the WOW field trip to report to the back of the school. That's all freshmen who are going on the WOW field trip, report to the back of the school. Thank you.
You know how you can distribute with multiplication like we did up there? Isn't multiplication or division just the inverse of multiplication? So you know what you can do with division? Distribute it. What's 2 divided by 2? 1. What's 2 divided by 2? So 1i. So could I simplify it? Yes. Now, I'm going to concentrate over here for a second with that vertex form to show you why I really like that vertex form. I know, that camera is real scary, isn't it? Alright, so let's look here. This is what a lot of groups, or these two groups over here did. Talking about this vertex form. Notice they found their h opposite of b divided by 2a. Substituted it in. They got k as 1. And I'm moving quickly, I get that, but look. They got their vertex form. And then what did they do once they started getting their vertex form? Leah, what did they do from here? Once they had vertex form? I watched you do it. You did, I watched it. Vertex form, what did they do to start solving this equation? They what?
I don't know what it's called.
Oh, we gotta learn what it's called. This language is important. Huh? Is it an inverse?
Yep, right, inverse.
Was this an inverse? Is that what they did?
Yes.
1 minus 1 is 0. That's the inverse, right? They cancel each other out, creating that 0. So make sure we learn that language, right? Inverses to undo things. We're going to literally study what are called inverse functions in about 2 units. So we need to be familiar with what an inverse operation is before we get to an inverse function. Okay? So those inverse operations, undoing things. And then 0 minus 1 is negative 1. So I just want to pause here and point out this is what they had. What do they need to do next? Square root. Okay? So what does x minus 1 equal? Thank you. We took that square root, so it's got to be a positive and a negative. So what is the beauty of using the vertex form in this problem? It's easier? Maybe? What do we not have to do as much? What do we have to do with the quadratic formula that we didn't have to do here? Starts with an S. We had to simplify a lot with that quadratic formula, didn't we? Did we have to simplify with this vertex form? And that's not guaranteed every time, but that is something to be aware of. That's one of the reasons why I like the vertex form. It requires less simplifying to finish solving it. Those are just things to consider. Could you still use quadratic formula?
Yeah.
Yes, but this simplifying, or there's less simplifying here. All right, what questions do you have about this problem? Okay, now, the last thing I do want to point out is, if you look at the first page, not the first page, page 107, part B, it asks you to talk about the what. It says determine the what there. Discriminant. Oof, another vocabulary word. Okay, so let's talk about that discriminant. They give you even a little note, don't they? What do they say the discriminant is?
Of the function is b squared minus a.
So, what do we mean by discriminant? Anyone recognize that thing? It's the, looks like what? Okay. Does anyone recognize that discriminant? Oh, thank you. We gotta recognize immediately, that's from the what? Quadratic formula. Specifically, it's which part of the quadratic formula? It's the what? It's not the whole top part.
Oh,
It's the what? It's that radicand. Come on with it. Now, I want to point this out, and I want you all to note this, and then I'll give you a couple of minutes to write what notes you need to. Hey, does anyone recognize this right here?
Yes.
That's how we find
That's right.
Oh, that's the H from the vertex, right? Hey, because what's right in the middle, guys? What's in the middle of your quadratic? Guys, what's in the middle? Say it louder. The vertex, right? And if I take, let's just make up a number, -3 plus or minus 2, then -3 plus 2 is -1, -3 minus 2 is -5. Isn't -3 right in the middle of that? So the H is the middle, and then we add and subtract that square root to get to our roots, okay? That's where that's coming from. It's not random. You see that? Lee's like, oh, that makes sense? Is that, you're like smiling about it? It's exciting. I'm glad to see that.
No,
You don't like that?
No, I'm laughing at you. I'm sorry.
What would I do now?
No, it's like the way you pointed at it. It's really funny to me.
Okay, I'm glad that at least that was funny. All right, so we got our H here. We're adding and subtracting those things. Now, the reason why they asked you to look at your discriminant, I want you to think about this. In this problem, b squared minus 4ac was -4. By knowing that the discriminant, that radicand, was -4, what do you know about that quadratic or about your zeros? What do you know about your quadratic knowing that b squared minus 4ac was a -4? They're what? Oh yeah, we're going to take the square root of a negative, right? So they would have to be what kind of zeros? Imaginary. If your discriminant, your radicand in the quadratic formula is negative, then what do we know? Imaginary. If your b squared minus 4ac is negative, then you have imaginary zeros. That's huge to recognize. That discriminant tells us a lot. Now, you don't have to memorize that, but that is a good note. It can help you a lot. In a similar way, if b squared minus 4ac is equal to something like 9, can you take the square root of 9 easily? So you're going to get rational zeros if you can easily take the square root. But if b squared minus 4ac equals something like 27, can you easily take the square root of 27? So what kind of numbers, what kind of zeros are you going to get? Say it again. Irrational, right? By understanding discriminants and understanding radicals and radicands, you can easily figure out what type of roots you're going to have and what method might be the most efficient. That's just something to attend to. So if b squared minus 4ac is equal to a negative, you're going to get imaginary zeros. If it's equal to a perfect square, you're going to have rational zeros. And if it's not a perfect square, it's going to be irrational zeros. And so I just want to point that out because that is a useful tidbit. I'm going to point this out though. Do you have to know that? No, because if you just solve it, you're going to find out what kind of roots you have anyways. Okay? My teachers made us memorize it. Why? I don't know. It's cool because I love math and I'm a giant nerd. But if you just solve the equation, you'll know what type of zeros you have. Okay? Alright. Take whatever notes you need to about this problem. If you want to make notes about the discriminant to help you in the future, that's great. If you want to make a note about viewing the quadratic formula here, maybe simplifying that radical, go for it. If you want to make a note about that vertex form, go for it. Don't forget that vertex form I do love because there is less simplifying in that vertex form. And go. By the way, I do want to say, that was some of the best stealing of ideas and figuring stuff out from like one group to the next that I've seen in a long time. It was great, thank you. I appreciate it. Staying on task, trying to figure stuff out. It was awesome.
Miss Candy, you
Yeah.
like what candy?
Say it again,
You
Peyton.
love about candy?
You think you deserve candy?
Yes.
What type of candy do you want?
Reese Cup.
Too bad, I ain't got none of those. I did buy some Starbursts so that when I hear some really good questions being asked, I can pass those out, but I gotta make sure I hear some really good questions.
For real, I'm not joking, like, I really wanna know, is that the end, like, is that the answer to that problem?
The 3 root 2I? What do you mean by the end?
Like, is that the,
It's just like, so.
the answer?
I mean, here's the thing.
Like, could I keep going is what I'm asking.
Yeah. Square root of negative 18 is the answer. 3 root 2I is the answer. These are just equivalent forms. I would stop here, because you could take the square root of 2 and get a decimal, but it's gonna be an irrational number. Can you write an irrational number out in its entirety? Because that decimal continues forever and ever and ever and ever. So instead of writing an ugly decimal out, just leave this 3 root 2I. Now, I will make this note, with our imaginary numbers, I need to see the I. I need you to rewrite it with the I. So, I will say this, if you just take this and you rewrite it as the square root of 18I, I'll accept that for like a CE, because if you're solving, right, and you get to here, do you have clear evidence that you understand how to solve that equation? Right, that's the priority. To get to that CCC or CCC plus, you have to be able to get to this point because that is a part of that simplifying process.
What?
Turn around.
And a lot of colleges are gonna require that. Yeah, a lot of college classes. Pre-cal, Miss Beasley, I think requires that, so. Yeah. Okay. Today, we're gonna focus on those complex numbers, so solving quadratics with imaginary zeros, roots, solutions, fun things like that. Does anybody need more time to write their notes? I see Drake writing a little bit.
I got a question like this. Who is Mr. J? Mr.
Dog, for real?
Mr. Aubrey.
I see how he went, I see how he
Yeah.
I didn't know that.
He's going
He
Friday.
got called Mr. Aubrey. He said.
Oh,
Aubrey.
It's the way that it's.
I thought it was spelled that age.
Miles.
You know, like Jose be spelled with a J.
So today we're on imaginary numbers. We're going to start classifying numbers over the real number system, simplifying square roots. Again, that's foundation pieces. And we have these mathematical terms that we need to get comfortable using, describing those numbers. A lot of those are just the different number systems. But what we're trying to get into is adding, subtracting, and multiplying imaginary numbers, graphing imaginary numbers, which I know it's like, Mr. Kenny, we just said we can't graph imaginary roots, right? But fun fact, there's a number system that includes the imaginaries. Super easy though. And imaginary numbers also are really useful in context of like vectors. So like, have any of y'all taken physics yet? No? Yes? Y'all talk about vectors in your physics class?
Yeah, we talked about it.
Okay, so like vectors have direction and magnitude, right? Those imaginary numbers can describe both of those things, and so imaginary numbers are really useful there. There's a whole lot of applications of imaginary numbers. Anyways, simplifying square roots with negative radicands, classifying numbers over the complex number system, all those fun pieces. Really quickly, I do want to ask, oh, crud. I just noticed something. If you look on this part of your proficiency scale, I put the same thing twice. I put a real part of a complex number. The other one's supposed to say the imaginary part of a complex number. So if you look at your proficiency scale on the complex, so not the real solutions one, the second side, and it has imaginary solutions. Where it says real part of a complex number twice, the second one should say an imaginary part. Which, I just want you all to think about this logically. Anybody know what the real part of this imaginary or complex number would be? The one? What's going to be the imaginary part? The I, okay. So just want to establish that. 1 is the real part, I is the imaginary part. We're going to talk about those terms later. Yes, Taylor. Okay, I'll look for that in a second. All right, here's really quickly 5D. Describe how you can check your solutions. How can we check to see if 1 plus or minus I is correct? How could you check to see if 1 plus or minus I are your solutions? Davis, do you remember what the term solution means in mathematics? It's a very common misconception, and hopefully your solution is the answer, or hopefully your answer is the solution, but we need to learn this term backwards and forwards, because in mathematics when a teacher says this, on the ACT when it says this, on anything, when they say the word solution, they actually only mean one thing. Say it again. It makes the equation or makes the inequality true. So if we're going to ask, hey, how can we check our answer, what can we do? Type it into the calculator, right? While I'm looking for this proficiency scale for a couple people, I want everyone to pick up a calculator. I want you to type. So remember, we're looking at 0 equals 1 plus I squared minus 2 times 1 plus I plus 2. Type that into the calculator. See what it says. Check it with the 1 minus I. Yeah.
Was that just you taking it with the tail? Like, what's the real line?
This right here. That's part of the vocabulary for this.
Yeah, that's all that.
Yeah.
It's a true.
Say true.
Because you need to know.
Anyone else need the proficiency scales for this unit? Oh my gosh.
But I think I got one.
Thank you.
Yeah. No idea. Last week's was that.
Mine's the
It's two-sided. Real and imaginary. All right. What did it say? True. Let's check 1 minus I. Let's make sure that one works. You just did 1 plus I, right? Now, hold on a second. I just want to point this out and remind you. Instead of making your life hard and typing the whole thing again, so Leah, hold on a second. One thing you can do is you can just hit the up arrow until that equation is highlighted. And then hit enter. And it brings it down. And you just go and fix what you need to change. So use that. Guys, that's one of the best features of these calculators and really powerful for the ACT. Yeah, dog, you can use these calculators on the ACT.
That's how they told me.
Yeah, 100% you can use them. There is a version of this that has what's called a computer algebra system, CAS, and you cannot use that one.
What's the second?
It says true again, huh?
Well, never mind. You got it.
Say again, Peyton.
I was asking what was the second one, which was mine, because I was trying to put my paper.
1 minus I. Remember, it was 1 plus I and 1 minus I? Yeah. It says true for both of them. Oh yeah, because we're supposed to have how many roots? 2. Yes, Shadidra.
It all makes sense.
Say again. Then you probably typed something in wrong.
Don't make me mad.
You didn't put the I. No, remember, it's I. I is the square root of negative 1. I and negative 1 are not the same.
Well, 1 minus
Well, I'd rather have it in.
I've been a child.
You know, you got something to me.
Yes, ma'am.
It say false before.
Y'all help each other out around the room if someone next to you is not getting it right. So it has to be highlighted. So
You get it right?
see how it's highlighted now? Hit enter.
And
then go change it.
Oh, that's so.
Okay.
So you did talk
I'm gonna come around and check and make sure that everyone has it correct. Type it in the calculator. But while I do that, I do want you to go to your vertical surfaces quickly, and I want you to work on number 6, where it says use your answer to question 5, part C, to write that standard form h of x in factored form. Use your answer from 5C to write that standard form into a factored form. Let's get up. Let's get going. Yeah. All right. Was everybody able to get into the calculator? Okay, so we'll see in the
Mr. Kenny.
Remember the solutions that we found for that problem? The 1 plus and minus i?
Mr. Do you
wanna
put
call
this
it
also
here?
over here?
You can stop it.
How do I do that?
So we're on the back right.
And help us with this problem.
Yeah.
Like variables not being defined. Hey guys, if our factored form and our standard form are, if our factored form is correct, what should we call those two equations? No. If our factored form and our standard form are the same, they're called what? Say it again. Equivalent, right? Same inputs are going to map to the same outputs. How can I see that? Say it again. Graph it. Guys, if I want to check for equivalent functions, I'm going to graph those jokers. X squared, was it minus 2x plus 2? So there's that one. Notice it has all the features we expected it to have. And now x minus 1 plus I, which remember you have to go to the number I, not the letter I. And then x minus 1 minus I. So it's the same. Now, one thing I'm going to caution you is we got a little lucky with this one. So, because the roots were the same, that's what I mean by this. What really we should have done is x minus 1 plus I times x minus 1 minus I. That's really what's happening here, because I'm subtracting the entire root, so I put that inside parentheses. Notice, because I did it like this, I end up with x minus 1 minus I and x minus 1 plus I. Notice that came out to be the same as what we saw, but if you don't put it inside of parentheses like that, it can mess up sometimes. Okay, so that's just one thing I would caution. But notice, that was a pretty simple check, wasn't it? This is why we need to be able to recognize those concepts of equivalence. Oh, they are the same. I'm going to graph my two functions and see if they're equivalent. We good with that? You good, Davian? You look real hype. Okay. All right, questions about this problem?
No.
Davian, you got a question? You look like you got a question.
I don't.
You sure?
Yes. Yes,
Huh?
I'll got a question.
Okay. All right. So, moving forward. Oh no, there it is. All right, so we checked our solutions, all those fun things. I want to come back to these problems, so I'm going to leave these until later for practice. And so here's what I want to talk about. This is 6.2, page 97, if you want to turn there. Okay? Okay. So, these are the different types of numbers. Notice we have all of our real numbers in comparison to our what? See how those are separated from each other, right? We got real, we got imaginary, and what do they both fall under? Complex. So, all numbers are going to be called what? Complex numbers. All numbers are going to be called complex numbers, right? So every real number, every imaginary, it's complex. Imaginary is going to be when we have what involved? So if there is an I, so if there's an imaginary component, than imaginary. So notice we use that capitalized I to indicate what number set. Imaginary, right? Notice what letter do we use for complex numbers? C. By the way, you can always write the word out or you can learn the symbols. I will accept either. You still need to be able to justify. So what do we use for real numbers? R. Right, that makes sense.
Do we have to put on a squiggly line too?
So you talk about, so this is what it's written as, like that. I do not expect that. This is called Blackboard Bold. So like when teachers only had blackboards, when we didn't have computers, they wrote like this to indicate that we're talking about real numbers. But you don't have to do that for me. That's where that's coming from. Okay? Now all of a sudden we get to rational numbers and we use a weird different symbol. Q. That's weird. Why do we not use R for this? R is for reals. We already used it. Now, to help these things make sense, because it took me way too long to learn this, my teachers made me memorize it. Q stands for quotient. A quotient is when you're dividing things. So rational numbers are quotients. That's why it's a Q. That makes sense, doesn't it now? Yeah, they're not random. We go with rational. We talked about rational a good bit. When I say rational, what do I mean, by the way? It's a ratio of... So would this be rational? That's a ratio, isn't it? So is it rational? Why don't you type pi divided by 3 in that calculator?
Because the decimal keep going.
I was saying, that decimal is going to keep going, isn't it?
Right.
So are all ratios rational numbers? So it has to be a ratio of integers. Has to be a ratio of integers. To be a rational number, it has to be a ratio of integers. As soon as you put a non-integer in there, an irrational number, it's going to be irrational. Miles, you good with that?
Can we please get Lenny Howard to the office for checkout?
He's on his way. Just be aware you're going to miss the imaginary number stuffs. So you'll want to catch up on that. It's just the next few lessons is actually one of the easier lessons to miss.
You should have just stayed home.
That's like 6 out of 5.
It's not on.
I know. Alright, so rational numbers, we use Q for quotient. Do you have to memorize that Q? If you just write out rational, am I good with that?
Yep.
Yeah, so you do you. You'll always see me use Q because I'm lazy and mathematicians are lazy. That's why we have symbols for things. But no, when I use Q, I mean what? Quotient or rational, right? Okay, so what in the world is happening here with irrational? Why do we not just use an I? I is imaginary, right? Some people you'll see use I for irrational. Don't do that. What is this? What do you think this means? That's the real minus the rationals. So if I take the real numbers and I take out all the rationals, what am I left with?
Irrational.
That's what that means. That literally means, hey, I have the real numbers, I'm taking away all the rational numbers, so I am left with the irrational numbers. So, take your reals, take away all the rationals, you're left with irrationals. I do want to clarify a little bit, what are going to be irrational numbers? Like, what are some examples? 3 is irrational?
No, it's not.
Well, does anyone know where 3 would actually fall here? It is a whole number, but there's something even more specific. Natural numbers. Remember, where do we naturally start counting? 1, 2, and then what? 3. So you see how that's going to be a natural number? Okay? Come on, somebody give me an example of irrational. I already gave one.
Pi.
Oh, thank you. Pi. Most famous of all irrational numbers, pi. There is one I introduced yesterday when Mr. Javi was here, Euler's number. You don't have to know that one yet. It's just So Leonard Euler was one of the most famous mathematicians probably ever. And so he discovered or really found the properties of E more than anyone else. And so, yeah, Euler's number. Or natural number, or just E. But
Oh, that's that E in the calculator.
that's that E in the calculator, yes sir. How about this, square root of 2? What's that going to be?
Like 1.414.
Yeah, but what type of number?
Oh, it's here.
Irrational.
Oh, that's going to be irrational? What's the square root of 4 going to be? 2, so is that going to be irrational? No, what about square root of 3?
Yes,
Irrational. What about say the cube root of 8? Anyone know what the cube root of 8 is? It's what? Say it again. It is 2, because what's 2 cubed? What's 2 cubed? It's 8, right? Okay, so the cube root of 8 wouldn't be irrational, but what about the cube root of 9? I don't know what that is. That's going to be some hideous decimal. Anybody starting to see a pattern for a lot of these irrational numbers? Where are we going to find a lot of our irrationals? Well, not just square roots, cube roots, fourth roots, fifth roots, when they're not perfect, right? So the cube root of 125 is 5. That's cool. That's an integer. That's a natural number. But if I ask you what the cube root of 127 is, you got the calculator. But do y'all know how to take cube roots in these calculators?
I do.
I'm still looking for it.
Okay, so really quickly, y'all see where it says x squared on the calculator right next to the 4? And what's in gray above that x squared? That's the square root, isn't it? Okay, but what's right next to the x squared as the big button? It's a little caret symbol for any power. And what's above that caret symbol?
It's 5.02653.
I'm looking at the calculator.
It's where? It's the
Hold
little
on.
arrow pointing
It's
out.
the one next to the
Man, you
square
said
root.
a carry.
That's what that's called. Have you
It's called a
never?
carry?
Yes.
I be using it. I'm sitting here looking for an
It's not. It's not a caret like C-A-R-R-O-T. It's C-A-R-E-T maybe or something like that.
I never heard it.
C-A-R-A-T.
I didn't either.
Okay.
This
I
even
just
on
saw
my
that.
phone, because, I mean, my phone.
How you go up?
Oh, and then you
How you
take
go
3 years. Yeah, it's 5.02653.
Have y'all not ever seen this in your English classes
Wow.
where you're like, oh man, I missed a word
Oh,
and
yes.
I drew all a caret to add something?
Oh, we think it's gonna call a carry.
That's right. Man, I'm shook that we have not learned that.
I thought that was.
Nah, we
I
just-
thought
It's called a
it was,
carrot.
We didn't learn
Yeah.
about it.
I thought it was just called an arrow without. Oh, you talking about
It's got a name. Guys, everything's got a name. If you ever see something you're like, what do I call it? Make sure you ask what that name is because it's got a
I
name.
thought it was supposed to type in, the.
Oh, please don't. Ugh, don't say that.
Well, you care, but other
The
teachers don't
square
care.
root of 126.
Hey, quick question. Sorry, I actually didn't show it. Do we know how to find that root now?
Yeah.
Is there anyone who needs me to show how to find that root on the calculator?
You know how to do it. Just tap. You know,
So look.
I know, I was gonna.
So right here, right, so x squared, the square root's above it. The arrow, any power, above it in gray is any root. And so when you hit the control, and then the exponent, no, actually I have to have a calculator page.
You said control. How would you get 190?
I didn't type it.
No.
I didn't type it in.
So notice how it gives you a little option here to put a root in, okay?
So that would be 3
So it'd be third root.
And
of
then
9.
the decimal is 5.0265.
Yeah, what
So notice cube root of 125 is 5. That's because 5 cubed is 125. But notice that decimal, and I want to show this. If I go up and highlight it and hit enter, does that decimal actually stop at this 3?
No.
Do you think it actually stops at this 4?
No.
It just can't go to infinity, right? So, or an infinite decimal place.
What if you do that again? You still get more numbers?
Well, that's as far as this calculator can do. I might be able to change it so it can go to 12 decimal places, I think is the max that I can do. All right, from there, irrational numbers. So where's the largest set of irrational numbers going to come from? Our roots. that are not perfect squares or perfect cubes or perfect fourths. So our largest set of irrational numbers are going to come from those roots. All right, integers. What do I mean by integers? What are they? What are integers? Okay, well, whole numbers are whole numbers. So what are integers?
Our integers.
What are integers though?
Integers.
Okay, so let's define our whole numbers quickly. What's a whole number?
One,
Okay, 1,
2,
3.
3, 4.
but hold on, these are the same as my natural numbers.
Okay.
Oh, negative
I
and
heard someone
positive.
say
Zero.
0. Our whole numbers start with the number 0. Okay, notice it starts at 0.
Oh.
Natural numbers, we naturally start counting at 1.
So that means integers are the negatives?
So
Negative
it's
and
not
positive.
just the negatives,
Negative
Negative
and
and
positive.
it's the whole numbers and their opposites.
Opposite? Okay.
Yes. Integers are the whole numbers and their opposites. Okay. Now, one thing I want to point out, and I need you to notice this. Every natural number is also a what?
Hold on.
And every whole number is also and every integer is also and every rational number is a,
Real number.
right? So if it's lower down, it's everything above it. And so is a natural number a complex number?
Yes.
Yes. Is a natural number an imaginary number?
No.
No, right? Like those are on different branches. Okay? And that's why I say rational numbers are ratios of integers, right? Rational numbers are ratios of integers. Every rational number is a ratio of an integer. All right. I think that's all I need to talk about with those before we do some practice with them. Okay? I will let y'all ask some questions. What questions do you have about these different number sets?
None.
Crystal is confident, but
I think I'm
I got 20 other students in this class.
I think I'm good. I think I'm good.
You think you're good, Davian?
It's straightforward. Pretty straightforward. Mine, second, the same thing. We should be doing something. Right.
We'll come back to that. All right. So here's what I want us to do, and I'm actually going to make a few more examples to add on to this. I want y'all to classify these numbers with every number set that they belong to. And so I'm going to add in, so we go through what, F, so G is going to be negative 15 divided by negative 3. H is going to be the square root of 4 divided by 7. And, ooh, this is a good one. I is going to be I times I.
Wait, so
Those are the numbers that I want you to classify. So, at your vertical surfaces, I want you to take, let's say, 4 or 5 minutes, and let's classify those numbers, identify every number set that they can belong into.
Want me to stop recording?
Yeah, you can stop it. I was about to do that. We're focused and can ask the questions you need to ask. If I missed somewhere that we differed, let me know. But, all right, 2A, one of the things I did see is, well, by the way, let me ask this. What number set was everything in? Everything is complex, right? Okay, everything's in the complex number system. A was one of the few places I saw a little bit of difference. Most people included Q and R, but the 8s, y'all did not. Should we include Q and R for this number 3?
Yeah.
Why?
Because of, right?
So remember, and that's a good way to think about it, is it goes up the branch, right? So what is the most specific set that the number 3 fits into?
Natural.
Natural, right? And every natural is whole, integer, rational, real, complex. What I will point out is it has to be real because what does it not have? It doesn't have an I, does it? So it has to be real. Some people might look at that 3 and be like, oh, it's not rational, but Could I rewrite 3 as 3 divided by 1? Is that now a ratio of integers? Those would be equivalent, right? Could I have written it as 6 divided by 2? So it is a ratio of integers if you rewrite it. Does that make sense why it's rational as well? And again, if you just go up the branch, we're good. B, I think everyone did complex, real, and irrational. Did anyone get something different for B? Oh, that's right. Okay. And then, so for y'all, again, B, y'all didn't include the reals. But if it doesn't have an I, what is it? Real. And also, if you're going to say real minus rational, doesn't it have to be real? Right. So keep that in mind. Just think about all those number sets. C, the only options are imaginary, complex. D, I need to talk about this one, okay? Because this one threw a lot of us off. 5.45 repeating. I had a couple of groups do this. But if we take 45 divided by 99, what did we get for the groups that had to do this?
45, 45. And it keeps going.
And it keeps going. Please remember, rational numbers, the decimal can go to infinity as long as that decimal is what? Repeating. Rational is a ratio of integers. And if it's a ratio of integers, that decimal either repeats or it terminates. So as long as it's repeating, we're good. If you even look at 7/3, right? That's 2.3 repeating. As long as the decimal repeats or terminates, it's a rational number. You good with that? Okay. I think we're good on E. Didn't notice anything else. F, complex, imaginary. All right, so G, this is the one I want to start really talking about. Yes, ma'am.
Wouldn't G just be Z, Q, R, and C?
Why?
Because an integer is a negative. The whole numbers and the natural numbers, it doesn't include negative numbers. So wouldn't it just be integers,
Okay.
rational, real, and complex?
Anyone want to add on to or push back on that? So Crystal and her team argued that it was just the integers, rationals, reals, and complexes. Again, because you're thinking that those negatives are only the integers, not, because this group up here said whole and natural as well, right? A couple of groups said that. So does anybody want to push back on it just being integers and on up? Elizabeth?
We said whole and natural because whenever you solve it, you get 5, positive 5. Like negative 15 divided by negative 3.
I'm going to push back on your language a little bit. What are we solving?
Or just whenever you like simplify it.
There we go. Be careful. We don't have an equation to solve, right? But if we simplify it, and Crystal, I think this is what happened to y'all, you just miswrote it.
No.
Negative 15 divided by negative 3. What's a negative divided by a negative? A positive. So that is a natural. It is whole as well. We're supposed to be natural. Yeah, you're right though, based on what you wrote. But I will point this out. If you're on a test, simplify it and show your reasoning. Because if Crystal said, "Hey, these are negative, so it's only integers on up," that's very clear evidence of understanding. She just made a mistake on writing that down. Well, miswriting that is not the same as not understanding the number sets. That's part of the reason why I want you to justify your answers. All right. H. A lot of us had the same question. You're asking, hey, is this entire thing in the radical? Is that entire thing in the radicand? Well, did I write the entire fraction in the radicand? No, I was very intentional about that. I only took the square root of 4. And so if I take the square root of 4, what do I get? So what kind of number do we now have? We have a rational number, a real number, and a complex number. And I got you suckers good on I.
What you mean?
I got everybody.
Wait, what?
Hey, what is I times I? So, I squared, right? Hey, what is I squared?
Negative 1.
Sometimes you guys simplify your values. Notice I times I is imaginary, but if I do I times I and I get I squared is an integer. I squared by definition is negative 1. So what is I squared? Actually, that last one was all of these. So lesson out of this one. Listen, guys. The best learning happens out of mistakes. I did that intentionally so that I could draw this out. I was curious if we would notice that. Please make a note to yourself. You got to simplify your values. Simplify it to really figure it out. Because, yeah, we might naturally think that's imaginary, but it actually doesn't work out that way. Beautiful mistake. I love it. What? Yeah. Where does the best learning happen, Miles? Out of mistakes. If you're not making mistakes, you're not learning, you're just practicing. If you're not making mistakes, you're not learning, you're practicing. All right. I did not get a chance to make prayer models last night. I got home and I crashed. However, I'm going to start tomorrow assuming that you have done this practice and have asked the questions you need to ask. So this practice on page 99, I need you to do it and be prepared to ask the questions you need to ask. 99. You see those 4 square roots? That's page 99, right? Yep. By the way, notice the textbook shows simplifying that radical just like I do because it is hands down the most efficient method. I can't remember if I did that already or if I got it from the textbook, but it is the best way I've ever seen to simplify a radical. What questions do you have? We got 3 minutes. Go ahead and start on those, and that way you can ask questions. Yeah, you can pause it. So go